When we left off in topic 2.5, we knew how to take the derivative of a power function using what we called the power rule, and what we were left at is we were kind of staring down a polynomial, and we listed off some of the things that we needed to establish rules for in order to take the derivatives of polynomials. And you can see in topic 2.6, the title lists off the things that we needed to address. We need to address the derivative of a constant, how to handle sums and differences of functions, and then what to do with constant multiples. And rather than just give you the rules, I'd at least like to derive them because they're pretty straightforward to derive using the limit definition. And then we'll look at some examples and kind of tie this all together. But a lot of the rules that you're going to see in this particular lesson are actually really friendly for us. So we're going to use the limit definition of a derivative to prove the rules we're going to get for constants. That would be just a number. For example, what's the derivative of 7? And then also we're going to look at how to handle constant multiples. That's going to give us a rule that tells us how to handle a coefficient in front of a function. So I know how to take the derivative of x cubed, but what about 4x cubed, for example? So let's start off with constants. Let's let c be a real number. And this is going to be true for both constants and constant multiples. We're going to address them as just some real number c. Well, what I want to do is I want to find the derivative of c. So the derivative of some constant value. Again, the derivative of 7, the derivative of negative 4. Well, the derivative, if I use my limit definition of the derivative of c is going to equal the limit as h approaches 0 of f of x plus h minus f of x all over h. Well, let's think about what this is going to look like for my constant value c. Because it's constant, f of x plus h is just going to be equal to c. If I asked what's f of 3 of 5, it's 5. If I ask what's f of 3 plus h of 5, it's 5. F of x plus h for this constant is just going to be c. The same is also going to be true for f of x. It's a constant value, so it's going to be the same regardless of what input it takes. So I get the limit as h approaches 0 of c minus c over h, which is the limit as h approaches 0 of 0 over h. And yes, if I do direct substitution, that gives me that indeterminate form. But 0 divided by h for anything other than 0, which if we're talking about limits, we're not concerned about 0 itself, we're concerned about the area around 0. This is going to equal the limit as h approaches 0 of 0, which is simply 0. So what we just found out is that whatever the constant value is, the derivative of a constant is always 0. In fact, we can write that as our rule. The derivative of a constant value is always equal to 0. And that actually makes sense if you understand the vocabulary of derivative and constant. If I say what's the derivative of a constant, I'm asking you what's the rate of change of a constant value. Constant by definition means it doesn't change. And so the rate of change of a constant is always 0. And that's what this notation and that's what this little one-line proof here is suggesting. So for example, if I want to know what's the derivative of negative 5, well, the derivative of negative 5 is just simply 0. So whenever we are using our derivative rules in concert with each other, if I want to know what the derivative of a constant is, it's always going to be equal to 0. Now let's take a look and see. We're going to let c still be a real number, but now I want to find the derivative of c times some function f of x. And this is going to address when c is serving as a constant multiple for a function. That's going to be what allows us to take advantage of this rule to figure out how to handle coefficients. And again, I'm going to apply this to my limit definition. Well, this is equal to the limit as h approaches 0 of, I've got c of f of x, so I'm going to have c of f of x plus h minus c times f of x all over h. And now we just kind of need to understand what we can do, one, with algebra, and 2 with limits. And we've talked about the algebraic properties of limits and how they're very nice. If I look at the numerator here, I've got a c in common. So I can actually factor a c out of both terms in the numerator. And because c is some constant value, we know with limits that it can actually be removed outside of the limit statement. So I can do a little rewrite here of c times the limit as h approaches 0 of f of x plus h minus f of x all over h. So again, just factoring this c out, and then because it's a constant, it can go outside the limit statement, and I get this expression right here. Well, take a look at this right here. The limit as h approaches 0 of f of x plus h minus f of x over h. That's f prime of x. So I can say that this actually now equals c times f prime of x. And what the rule comes down to is I can just very plainly state that the derivative of a constant multiple times a function is equal to, I can kind of do the same thing with that I did with limits. I can take the constant multiple and remove it outside the derivative statement, and then multiply it times the derivative of f of x, which we note as f prime of x. And the notation, if that's overwhelming you, it actually is going to be what allows you to kind of do intuitively what you'd really like to do. So the example here is, let's do a power function with a coefficient now. Let's say I want to take the derivative with respect to x of the function 3x to the fourth. Well, what this now says is I can take this 3 and I can remove it outside the derivative. And so I can say this is 3 times the derivative of x to the fourth. Well, the derivative of x to the fourth is 3 times 4x cubed. And so this ends up equaling 12x cubed. And if you take a look at what we started with and you really understand what the power rule is saying, you can look at this 3x to the fourth. I can take the power 4, multiply it times 3 to get 12, and reduce the power by 1. So this, in some ways, in terms of how we apply this constant multiple rule, is really going to just be kind of an extension of the power rule, if you will. We're going to be able to pretty quickly go from 3x to the fourth and get to 12x cubed. But these are the rules, or that's the rule that's going to allow us to do that. And then we also have the fact that the derivative of a constant is equal to 0. And after we look at sums and differences, we'll kind of add all of these rules we've learned between 2.5 and 2.6, and we'll start taking the derivatives of some polynomial functions.